Ignition sequence start.
Good morning. Here's the scene inside the International Space Station Flight Control Room at NASA's Johnson Space Center, where a team of specialists is always on duty to monitor operation of space station systems and work with the Expedition 64 crew members through the tasks of their workday in orbit. Commander Sergei Ryzhikov and his American, Russian, and Japanese crewmates are keeping one eye on their ongoing work of groundbreaking science research and space station maintenance, and the other on the series of ongoing spacewalks, which kicked off today and picks up again on Monday.
Houston Station on Space to Ground.
Welcome to Space to Ground. I'm Katherine Clayton. This week we had a spacewalk and settled in for story time. NASA astronauts Michael Hopkins and Victor Glover completed the first spacewalk of 2021 on Wednesday. The duo worked on installing power connections to the Bartolomeo science platform, which hosts payloads for scientific research. 2 of 3 bundles of cables for Bartolomeo were connected. The time ran out before a third bundle could be hooked up. It will be attended to on a later spacewalk. The astronauts also installed a Ka-band terminal to enable independent, high-bandwidth communication links to European ground stations from the Bartolomeo platform. This was the first spacewalk for Glover and the third for Hopkins. Stay tuned because Mike and Victor will conduct a second spacewalk together on February 1st to complete long-term battery upgrade work. NASA and Boeing recently announced a new date for the next Starliner flight test. NASA and Boeing are targeting March 25th for the Boeing Starliner's second uncrewed flight test. The Orbital Flight Test 2, or OFT-2, is an important step forward in NASA's Commercial Crew program. The OFT-2 mission will launch the Starliner on a United Launch Alliance Atlas V rocket from the Cape Canaveral Space Force Station in Florida. It will then dock to the space station and return about a week later. This test flight is a critical milestone in order for Boeing's Starliner to fly crewed missions to the International Space Station.
Space to Ground.
What brings you out here? Mr. Krill whispered quietly. We're looking for a superhero, Willow stated, quite mightily.
On Tuesday, NASA astronaut Shannon Walker read Willow the Water Bear by Houston Kid live from the International Space Station as a part of Storytime from Space, a program that combines literature with science. Kids and families can enjoy a great book read by an astronaut on station, as well as science demonstrations that complement the science concepts in the book. The program is sponsored by the Center for the Advancement of Science and Space, and the videos of the stories and demonstrations, as well as the curriculum, are all available for free on the Storytime from Space website. That's it for Space to Ground this week. Thanks for watching, and we'll see you next week.
Around their support for the spacewalks, Expedition 64 crew members have remained focused on their work supporting one-of-a-kind scientific research in space. It was more than 4 years ago that flight engineer Kate Rubins became the first person to sequence DNA in space. So last week, when she moved space science forward again with another crucial milestone for microbiology, the research team here in Houston took a moment to recognize Rubin's spot in scientific history.
Kate, while you do that, I have a few words for you. So today marks 4 years, 4 months, 3 weeks, and 5 days since one monumental jump of paradigm-shifting spaceflight science occurred when you, for the first time, sequenced DNA beyond the bounds of Earth. Since that time, 6 of your crew members have advanced that work and demonstrated significant advancements in microbiology through culture-dependent and culture-independent identification of microbes, human diagnostics when native RNA was prepped and directly sequenced on station, and in fundamental biology when sequencing was used to assess DNA repair following cellular transformation and CRISPR-based DNA damage, all on board. And that came from the minds of a team of high school students who won Genes in Space. Your work revolutionized space science, and today marks another significant achievement with the collection, preparation, and sequencing of highly complex and multiplex samples. On behalf of the biomolecule sequencer team, aka Menanti, myself, Sarah Stahl-Ramo, Aaron Burton, and Kristen John, and the whole spaceflight science community, we thank you for continuing to push space science through your work on board and through all you do to socialize and emphasize the importance of molecular biology in space. Thank you, Kate.
Oh my gosh, you guys are going to make me cry. This is so cool. I'm just incredibly excited to see this, and I've been talking about multiplexing for years, so this is amazing that you guys have been able to do this, and it's really, really, really fun to be at the pointy end of this spear here and to get a chance to do the sequencing in space. So I'm very excited about this, and I can't wait until we're multiplexing 96 well plates and swabbing everything on the space station.
That's where we're headed next.
The microgravity environment of the International Space Station provides scientists with a place to do research in many different kinds of science. Fluid physics is one of them. And last year, flight engineer Doug Hurley gave a strong squeeze to a plastic bag as part of a simple experiment to learn more about how to manage liquids in microgravity.
Mark, station on 3, how do you hear? This is Doug. Doug, I got you 5 by 5.
We started maybe 15 years ago in this long line of experiments that have been going to space that are all small-scale fluids experiments that have really taught us a lot about managing fluids in space without any moving parts, without any electricity, just fluidics. Now we can apply research results that we've learned from doing experiments in space to actual space systems that actually require gravity to be gone for them to work. That's different. That's a new horizon, I would say.
Okay, Mark, ready on step 4.
This is an engineering demonstration of a wastewater purification system. So inside that foam, there are all these weird channels and different wetting foams in there, such that capillary forces wick the liquids out, opening the channels up. So it's a capillary solution to an engineering problem of managing brine and contaminated water streams.
Yeah, it sounds really, really interesting and frankly really cool. I can't wait to see what it does.
What you're going to do is you're going to open that little valve out of the drink bag, and you're going to prime the tube. Then you're going to squeeze that bag, the drink bag, and then kind of in about 15 seconds fill the entire foam with the contents of the bag.
The interior piece of that foam is highly wetting, so it wants to suck up that water. But then there are pieces on the outside that are hydrophobic, so it doesn't want the water to penetrate through. So how can we, mix that up? What are the issues? What does that look like? Because ultimately this piece of technology, even though it's so simple as a piece of foam, it can potentially do so many things.
If you watch the videos, you see it, you're going to think it's dull and what are these goofs doing? You're going to say that. But basically what it is it's a dyed liquid. It's actually red fruit punch that we use, which is a simulant for urine.
You like the backlight view?
Yeah, we're geeking out over that. It gives us the complete view of this whole thing. It's nice.
That's pretty cool.
So the purpose of this experiment is to see how well does the foam hold the liquid in microgravity, and if we completely agitate it and really put this piece of equipment through the ringer, how well does it bounce back? Honestly, the most surprising thing that's come out of it is how simple we can make this technology. Maybe the foam project is going to enable a backup system for the toilets, or maybe it's going to be a new wastewater processing system altogether, and that's just the future. It's just, it feels like anything is really possible.
We are very hopeful that our work, which started out in fundamental research and is turned more and more applied, could actually get to the point where it's delivering on equipment. Equipment that functions without moving parts, or a minimum of moving parts, without power, without noise. We'd love it to have a system that just works passively by its shape. And whether it's on the moon or in orbit around the moon or in way to Mars, we'd love to contribute in that way and in the way that makes others able to do that too. So by publishing the design laws, by the design experience, by the experiment experience. We'd love to do that too.
I think it's just cool. It's so simple and it's so cool.
Scientists are using the International Space Station to develop robots that can take care of simple tasks so astronauts have more time to take care of the things that only astronauts can do. Astronaut Chris Cassidy gave us a look at his work with 3 flying robots being developed by NASA's Ames Research Center.
The unique thing about this particular one on the right docking station, it goes in upside down. Went and got some snacks, some nuts and some hot chocolate. So the scientific team is in California, the payload control center is in Huntsville, and of course I'm here. So we've got 3 different locations, we're all working together.
In more than 20 years of continuous human presence on the International Space Station, more than 3,000 science experiments have been conducted. Just in 2020, that included everything from growing radishes in microgravity to capturing 360-degree video footage of life aboard the station to monitoring our planet down below. Have a look at some of the highlights of the past year of research that's benefiting people on Earth while helping prepare us to explore farther into space. The structure of the International Space Station relies on a series of trusses engineered to withstand the different forces the station may encounter at any time in low Earth orbit. In this demonstration video, astronaut Ricky Arnold explains the significance of these resilient structures and the forces they're up against in microgravity.
Hey there, I'm NASA astronaut Ricky Arnold. Welcome aboard the International Space Station. Today we're going to talk about the Space Station Truss. The truss segment is just about 100 meters from side to side. A truss is a segment or part of the whole integrated truss structure. The trusses are used to support the 16 solar array panels, which provide energy for us, and radiators which get rid of excess heat that builds up inside the space station. The design of the truss involves triangles and beams, which can be seen on Earth in structures like bridges. Why triangles? Well, this is because of their unique geometric properties, their methods of transferring loads, and their spatial openness. Triangles are more rigid than rectangular shapes because they have fewer joints. The larger number of joints in a shape, the more prone that shape is to being impacted by shear forces.
What I'd like to talk a little bit about today is some of the forces that can act upon the truss. Well, the first force I want to talk about is compression force. And compression force is just like it sounds, two things coming together. So if we apply a compression force to the truss, what do you think is going to happen? Well, let me go ahead and do it. And you can see right here where the truss would bend. What do you think the opposite force of compression is? Now, it's going to be pulling apart. We call that a tension force. And a tension force is what's going to help maybe even rigidize the truss segment, but it also could potentially pull it apart. I'm not going to pull apart this tape measure because we probably need it later for some work we have to do.
Now, if you look carefully, this next force I want to talk about
is basically kind of like a twisting force, and we call it torsion. And even when I just let go of the tape measure, you can see it will actually start to happen a little bit. You can start to see, because the center of mass is actually right here, where most of the tape measure is located. And when I let it go, the tape measure itself starts to twist just a little bit. Finally, the fourth force
that can act along a truss segment
is that can occur at a single point where two opposing forces work on a single point along the truss, just like they can upon the Earth's surface. Think about some earthquakes. You can have a plate that is, or along a fault line where one side of the fault line is moving upward or being forced upward while the other side is moving downward. And that force in one point in opposite directions is called a shear force. And we can also have that happen on the truss segment. Something like this.
One thing to think about, where do these forces come from?
One force, even though we're up here largely out of the Earth's atmosphere, we do still have drag with the Earth's atmosphere, which can impart loads on or impart a force on the truss segment. Another, I already hinted at earlier, is crew working inside. We're up here, we're exercising, we're moving really heavy pieces of equipment around. So we have an amazing engineering team on the ground, and we have specific disciplines their job is to monitor all the forces imparted upon the International Space Station. They keep track of all those various forces I talked about and where they could be coming from, the atmosphere, visiting vehicles, or even things that the crew are doing inside the space station, and to make sure that those forces aren't significant enough to cause any damage to this wonderful laboratory and living space we have up here in low Earth orbit. Thanks so much for joining me today. We'll see you next time. So long.
Lessons from space, like the ones Ricky Arnold has taught, were designed to take advantage of the presence of a former classroom teacher as a member of the space station crew, who could help students and their teachers on the ground in their studies of science, technology, engineering, and math. It was an effort that was built on the example set by another teacher 35 years ago.
Reach for it. Presented by Science at NASA. In August 1984, President Ronald Reagan announced NASA's plan to send one of America's finest, a teacher, to space aboard Space Shuttle Challenger. Of 11,000 aspirants for the adventure, 37-year-old high school teacher Krista McAuliffe from Concord, New Hampshire, was chosen. As the first teacher traveling to space, she planned to conduct science demonstrations from low Earth orbit to get students, quote, excited about history, about the future, and about space, end quote. Tragically, Challenger broke apart soon after liftoff on January 28, 1986. There were no survivors, and McAuliffe's planned demonstrations were shelved. International Space Station astronauts Joe Acaba and Ricky Arnold have brought McAuliffe's mission full circle by completing and filming on orbit her envisioned lessons as a tribute to her legacy. U.S. crew members aboard the station have also performed and captured other brief, engaging lessons, or STEMonstrations. As part of the Year of Education on Station, NASA has made all of the demos available to classrooms around the world. Chromatography is one of the most interesting McAuliffe lessons Acaba and Arnold have brought to life. It provides hands-on activities for students to understand the importance of capillary action and chromatography and compare how they work in microgravity versus on Earth. Capillary action occurs anytime a liquid spontaneously flows into a narrow tube or porous material. It's how plants get water from their roots to their leaves. It's how our blood makes a round trip through our bodies. And it's how those paper towels soaked up the orange juice you spilled this morning. Chromatography is a technique that uses capillary action to separate mixtures so they can be analyzed. On Earth, chromatography is used for activities such as studying samples at a crime scene. Chromatography is an essential technique for spaceflight, too. For instance, keeping crew persons safe from contaminants includes analyzing unknowns, which can be critical on long space missions. An example of a Year of Education STEMonstration features NASA astronaut Randy Bresnik slingshotting objects of all sizes across the inside of the space station with a bungee cord. He's illustrating how Newton's second law of motion holds true in microgravity, just like on Earth. Simply put, Newton's law states that the greater the mass of an object, the more force it will take to accelerate it. Year of Education on Station also included more than 60 opportunities for hundreds of students and teachers to connect via in-flight education downlinks with astronauts aboard the space station for live question and answer sessions. Participants ask questions about all aspects of living and working in space.
Hi, my name is Ramsey, and my question is, have you ever had the idea to get a lot of water, pour it out, and see what happens?
See how it just sticks to my hand? It just waves there. It doesn't really go anywhere. It just sticks right to the surface, so I could drink my lemonade right from my hand.
How do you grow plants in microgravity without soil and water getting everywhere?
One of the plants actually uses pillows that are impregnated with moisture and the nutrients they need. We have another advanced plant habitat that I've been working on where there's a reservoir and the water, it's all very controlled, pretty much soil-free. The important thing is nutrients and water.
Hi, I'm Lexi. Would a yo-yo work in microgravity?
I didn't have a lot of time to practice, so here we go. My first yo-yo. So it works, but it's a little bit different. So thanks for the question and letting me find out if they do work.
With the Year of Education on Station, NASA's goal was to do what Krista and her optimism did so well: inspire students and teachers to, quote, reach for it, push yourself as far as you can, end quote. For more on NASA's Year of Education on Station, go to www.nasa.gov/STEMOnStation. For other inspiring NASA happenings, visit science.nasa.gov.
For all the years that men and women have flown in space, they have taken pictures out the window of their home planet. Those pictures are amazing, they're remarkable, they're astounding. But for the folks who took the pictures, it's still something of a strain to convey to us Earthlings just how miraculous that view really is.
When you look out into the depths of space, you realize just the vast ocean of darkness, and we're on this little island.
Without a doubt, when you are climbing on your rocket, when you're launching into space, when the engine cuts out and you get to look back at Earth, absolutely every sacrifice is worth it. Every dream is worth it. The entire road there is worth it. Every bit of it is worth it.
It almost, I dare say, grieved me to think about how in the world am I going to describe this?
I will never forget that sight. The thin blue line of the atmosphere, the curve of the horizon. That's when it became real. Really, at a gut level, I'm actually in space.
All life is connected on this planet, and everything I do is in one way or another going to affect someone else that I share this planet with, or some other creature that I share this planet with.
The most significant realization to me was looking out and realizing not how far I was from Earth, but how close I was to Earth and how connected I was to Earth.
I'd give a lot to see that view again.
If you want another look at any of the stories we featured today, you can always find them at YouTube and Facebook, where you'll also find lots of other great features on a wide variety of NASA topics. Be sure to look around. Now, if you're looking for good conversation about human spaceflight, check out Houston, We Have a Podcast, our weekly show talking to folks involved in all areas of space exploration. Today, Gary Jordan gets into the details of NASA's upcoming missions to the moon in a conversation with the Artemis mission manager, Mike Serafin. Go to nasa.gov/podcasts for this week's episode and all of our previous episodes. You will also find the full library of all NASA podcasts right there. They're all also on Apple Podcasts, Google Podcasts, and SoundCloud.